Okay, if it is working properly, then what we'll expect is the third output over here, we would expect it to be a high number. Remember, it cannot exceed 1 if it's a sigmoid at the end. So it may be 0.05, 0.12, third may be 0.9, but every other one will be smaller than this. So then the way we will see which one did it recognize is, whichever line number has the highest value, that's the digit it's recognizing. Okay. So if the third output is higher than all the other values, that means it recognizes 0, 1, 2. So it recognized 2 as the correct output, right? Okay. But for this to work, these weights and biases have to be adjusted properly. And we do it through the training data. Okay? So let me now briefly give you an idea of the training. Then I'll come and try to relate it to the PCA. Okay, so suppose we were creating a digit recognition system. Okay, then our x will be, as we discussed, 784 times 1. Right? This will be basically a vector with 784 values, essentially representing a 28 by 28 some digit. Right? Okay, then let's pretend we decided to use 100 neurons over here. Okay, then we further feed it through, and suppose here through another set of weights. If I call this W1, call this W2. Okay, here we have 10 neurons. Okay, so rather than, so as you can see, the number of weights over here will be 784 times 100. Okay, so to make our life easier, what we do is we store it in a matrix. So so all the weights over here will be stored in a 100 by 784 matrix. Okay, we could have done instead of 100 by 784, 784 by 100. Okay, that's also okay. As long as we are consistent so that when we multiply these matrices, we don't come up with invalid size in terms of the matrix multiplication. Okay, so the popular choice is when we create the weight matrix, size of output times size of input. So for this weight matrix, there are 100 things on this side, so the output is 100. There are 784 things on this side, so it will become 100 by 784, right? Okay, very similarly, let's go over here. What will be the size of this matrix? 10 on this side, 100 on this side. So 10 times 100 will be the size of the W2 matrix. Okay, how many biases will there be?
100 by
100 and 10 biases over here, right? Okay. So now what we'll do is we'll be given training data. So let's pretend we are given 1,000 digits. Like each one could be 0, could be 1, could be 9, could be 8, right? And we know, so we are already told the digit. So if it's a 3, as an example, the expected output is given to us. In this case will be 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, right? Because this, corresponds to digit 0, digit 1, digit 2, digit 3, digit 4, 5, 6, 7, 8, 9. So this is how the expected output will be if the input was given to us as a digit 3, right? Okay, so if we are given 1,000 of these type of cases, this is what we do. First, we train this neural network using this training data. So our training algorithm looks like this. For I equal to 1, 2, number of epochs. For j equal to 1, 2, training data size. Okay, so if we're given 1,000 training data, the j loop will go through. Okay, and before this, we will initialize WB matrices randomly. Okay, so now we'll feed, let's say, x of j to the network. Okay, and compute actual output. Okay, so what will be the size of this actual output in terms of matrices? If there are 10 neurons over
10
here,
cross 1.
so this will be 10 by 1. Right? Okay, so now based on a loss function, okay, do back propagation and adjust weights and biases. So this is how simple the algorithm is. Okay, I'll give you a tiny bit for the benefit of those not in deep learning, tiny idea of this, then I'll come to the PCA part so that you guys can see something new over here. Okay. Okay, so let's say we fed in digit 3, right, as an example. Okay, in the beginning, these weights and biases were initialized randomly. Okay, so obviously, it will not produce zeros and ones like we were expecting. It may produce the actual output, maybe 0.1, 0.2, 0.15, 0.8. 0. Let's say 32, 0.79, 0.81, and so on. So this is how the actual output will be produced. Okay, so in all of deep learning, okay, we have this. So there are two categories of deep learning. Okay, there's a supervised learning. And unsupervised. Okay, in supervised learning, we already know what the expected output is, so we can easily come up with a loss function. Okay, so the example we are doing right now is an example of supervised learning where we feed in a digit 3, we know this is the expected output. Okay, so a popular loss function. So loss or error function is basically a Euclidean distance between the actual and the expected. So our terminology will be, we will use the y to indicate the expected output. We'll use the letter A to indicate the actual output. Okay, so our loss function simply can be y minus a squared, sum over all training data. Sorry, sum over all outputs. So if I made it yi, ai, right? So then, for example, the error could be I equal to 0 through 9. So we'll basically do 0.1 minus 0 square plus 0.2 minus 1, minus 0 square, 0.15, 0.32 minus 1 square, right? So this is what we call the loss function. Okay. So based on some number that we got as the error or the loss, now what we'll do is we'll go backwards, we'll adjust these weights and biases, we'll go backwards, adjust these weights and biases, and then we'll feed in another one, produce the actual, compare with the expected, go backwards, adjust the weights and biases, and we'll keep doing this not only for the training data, not only for the 1,000 training data as an example that's given to us, but also we'll repeat the same process maybe 100 times or 50 times until the weights and biases stabilize. Once they stabilize, now the neural network has learned. Now we can feed in any unknown digit. We'll examine which one is producing the highest number. Whichever line it's producing, that's the digit that it recognized, right? Okay, so last detail here is loss function is easy. Compute the actual output based on the randomly initialized weights. Okay, then do a Euclidean distance, which is what we did over here, and get some error, and then based on the value of the errors, go back and adjust the weights. Okay, so our typical code for adjusting the weights and biases looks like this. Okay, remember we had W1 matrix, W2 matrix, B1, B2. This was 100 by 784, correct? This was 10 by 100. This was 100 by 1. This was 10 by 1. Okay, so when we adjust these weights and biases, our typical code will be W1 equal to W1 minus the learning rate times partial L over partial W1. So this is what we call the gradient. Okay, then W2 equal to W2 minus the learning rate times partial L over partial W2. Same thing for V1. Partial L over partial V1. Same thing for V2. Okay, learning rate is a constant. Could be 0.1, 0.05, something like this, right? So if we know partial L with respect to partial W1 or partial L with respect to partial W2, then it's easy. We'll keep adjusting these weights. We'll keep repeating this over and over until the weights and biases stabilize, right? So the hardest part is how do we compute partial L over partial W1? Okay, so in the deep learning class, as you guys have seen, let's say, forget the neural network. Okay, suppose we have a bunch of systems we are passing the data through. We compute some actual output, here's the expected output, here's the loss function, right? It doesn't matter how many things we are feeding the data through. As we feed the data through, we are multiplying by W1. We are adding, let's say, bias 1, W2, bias 2, and these could be matrices, W3, B3, right? Okay, so what we do is we use a chain of partial derivatives to find out this partial L over partial W1 or partial L over partial W2. As an example, the partial L over partial W1 will be, so we start from here. First we'll go partial L over partial A. So from here to here. Then suppose this output is called, let me call it Z. Suppose this output is called, let's say, P. This output is called Q. Okay, so then we go partial A over partial Z. Okay, then we go partial Z over partial P, and then partial P over partial W1. So one step at a time. L over A over whatever the previous output was, this over this over this, right? Until we get to the gradient we are interested in, then we stop. So we always go to the previous output, okay? Even though the weights are being multiplied to take us to the next output, but that's how we determine this gradient over here. Very similarly, let's say you were only interested in partial L over partial W2. So then what will this be? Partial L over partial A, correct? Then partial A over partial Z. Z is this previous output that feeds into this system. And then partial Z over partial W2. Okay. So let me see if you guys followed it nicely. Okay, suppose we have, let's pick a simple example. Okay, so let's say we were interested in finding the value of partial L over partial W1. Okay, and let me call this S1, let me call this S2. Okay, so, and we have a simple two-neuron system like this. So if we were to find partial L over partial W1, what will it be? So again, we'll compute the complete chain, right? First we'll go partial L over partial A times
Partial A over partial S2.
Partial S2, then partial S2 over
A1.
A1, then partial A1 over
S1.
S1, then partial S1 over
W.
W1. Now let's see if we can put all the values. Our loss is y minus a squared.
Divided by half.
Okay, so if we didn't put half, if we just left it like this, then what is partial L over partial A?
2 times y minus a into minus 1.
2 times y times a into minus 1, correct? Let's go to partial A over partial S2. If this is a sigmoid, remember for the sigmoid we said f prime x, so if x is the input, f of x is the output, then this was
F of x.
f of x 1 minus f of x. So what's the output over here?
A2.
A. So this will become a times
1 minus a.
1 minus a. So we are done with this part. Then partial S2 over partial A1. Over here, see if we write the equation for S2, what is this? A1 times W3 plus 1 times B2. Do you agree?
Yeah.
because that's what the neural network does, multiplies it by a weight, then we sum it. So what will be partial S2 with respect to A1?
The weight matrix.
This W3,
Yep.
correct? Okay, now let's go to the next one. So we are done. What is partial A1 over S1? Pretend this is the sigmoid.
A1 times 1 minus
A1 times 1 minus A1. Okay, and lastly, what is S1 over W1? Let's write the expression for S1. S1 will be X1 W1 plus X2 W2 plus B1. So what will be partial S1 over partial W1?
A. Input X1.
Just X1. Right? So now these are all numbers. So we know exactly what is partial L over partial W1. Let's pretend W1 in the beginning was randomly 0.3. This was randomly created to be set to be 0.3. Learning rate we already know is 0.1, right? So as we feed, suppose X1 was 0.2, this was 0.1. As we feed through it, would we know S1? We can plug in the numbers and we'll get some S1 value, right? Then we pass it through 1 over 1 plus e to the minus S1, and we'll know A1. Then we'll know S2. So all of these are numbers. All of these are numbers. So we plug in, this will give us a number. That's how we will adjust the weight. And we keep doing this until the network is trained. Okay? So anyway, that's how, based on some training data, we'll learn all the weights and biases. Okay, now 5 more minutes. Let me tie it to a little bit of the PCA so that for those of you who already know this was, so you have some more information. Okay. Okay, so suppose I create a network. We feed in 784 inputs. It goes to 100 neurons over here. Okay, so instead of trying to classify, okay, what we do is in the next layer, we put 784 neurons again. So not 10, but 784. So I feed in a digit 2. Okay, so the question is how, of course there will be weights involved over here, weights and biases involved over here. So what will be the expected output? Now there are 784 outputs, right? Pretend, and normally we scale it by 255 because in a neural network we try to keep the inputs 0 to 1. Okay, so suppose the first pixel was 100, so, or let me make it 255. Easy, or let's make it even more meaningful, 128. So as I divide by 255, what will be this number then? Close to 0.5, right? Okay, suppose the next number is 64. In terms of the pixel value, if I divide by 255, what number will I get?
Small.
Half of that, right? 0.25. Okay, so what we'll do is we'll create an unsupervised system, meaning we won't tell it what digit it is, whether it's 2 or 3. Whatever the input is, we make the output also the same. Expected output is the same.
Could you repeat that part?
Okay. We feed in a digit 2, right? We normalize the inputs by dividing by each pixel value by 255 so that it scales between 0 to 1. Okay, then if the first number is 0.5, second number is 0.25. Okay, the weights will be initialized randomly, but we have to know what are the expected outputs over here. So we'll make the expected output 100% same as the input. So if this was 0.5, this will be 0.5. If this was 0.6, this will be 0.6. If somewhere in the middle, this is 0.3, the expected output on that line also will be 0.3. So we are making it learn itself.
Oh,
Okay, so you might say, how would that be useful? So now let me show you. Suppose we go to PCA. What's one of the goals of the PCA? Isn't one of the goals of the PCA dimensionality reduction?
yeah.
Okay, pretend you've mastered all the math for the PCA. You are able to reduce it to 100 values. Okay, after we train it on many, many different inputs, take a look over here. How many outputs is it producing?
100.
So isn't that the same as what a PCA does? Okay, in fact, so there's many ways to view this. In fact, in deep learning, we'll be going quite a bit deeper into it with variational autoencoders and so on. But the very, very neat thing about this is such a simple system, meaning training is so easy. We feed in 2 produces 2. I mean the same pixels. We feed in 3 produces 3 after it has learned, right? So now, if you take a look at digit 2 as an example, are the pixel values around here important?
No.
Right? And that's what the PCA does too. When it compresses it to those values which are important. Okay? So in this case, automatically we are making it learn what is important, what is not important. Okay? Because think of it this way. This part is doing the compression. So compress from 784 to 100 as an example. Then what is this doing? It's doing a decompression. From those 100, and then it's reconstructing back to, so in fact, once you do your PCA assignment correctly, this is what you will do. You will come up with the 100, then from these 100, you will reconstruct the original face to see, does it really look like the original face? And you'll be surprised, it does. Okay. Which one is easier? Going through all the math and computing eigenvalues, eigenvectors, then the basis vectors, or simply create 100 by 784 network. Yes.
Wouldn't the PC be faster though? Because it doesn't have the training time. You already.
Yeah, typically we don't worry about the training time because even if the training takes 10 days, once we deploy it,
It's good.
it simply feed the input and it will give you, right? Okay, however, now let me ask you a question. Let's pretend we were successful, we created a 100 neuron network, 784 outputs exactly same as the input. We trained it on thousands of digits. It has learned, we fixed the weights and biases. Okay, what's our goal?
To test.
To recognize a digit.
Sure. So how
Right?
do we do that?
So how will you do this? You give it a 2, it gives you 784 different values.
I was about to ask that.
You're convert
But
that
some
to an
instructions, the outputs, both.
Okay, this is how we'll do it. Now, after you've made it learn, the decompression is not important. You'll remove the decompression.
You just
Okay.
forward pass, that's it.
No, there's one more step. These weights will be fixed now. You won't touch them because you made it learn
It's good.
the compression, right? Now you create 10 neurons over here. Train it again, but this time only adjust these weights. Don't touch these weights.
Oh,
Okay, now you'll compare it in those of you who are in the deep learning and maybe this class too. How does this compare to your original design, where we trained the whole system? So you'll see this will do a better job. Okay. So anyway, that gives you an idea of how deep learning is transforming the traditional, same way as you guys learn. I'll show you how will we create a deep architecture to do image registration. So all this, what was that, assignment 5 or something where you guys went through?
batch.
No, in the computer vision class, where you develop the image registration equations like A, B, T1, T2. Okay, instead of us coming up with all that math, we'll make the network learn A, B, T1, T2. So in some cases, as you will see, it's better to use the deep learning approach. In some cases, we need a hybrid. Okay, so it's absolutely essential to know what is the techniques behind. Further, the last comment, deep learning field is very new in the sense that we already have some very, very fantastic mathematical approaches that we have developed. For example, this Wednesday, I'll show you another approach called LDA, Linear Discriminant Analysis, which makes the PCA better. So how could we use some equivalent of LDA in a deep environment? Obviously, you have to know, first of all, how it works before you can, even attempt that. Okay, anyway, so there's a nice merge of classical and the deep learning techniques that we'll explore. So if you guys can once again make it to this afternoon's deep learning class, please be there. Otherwise, I'll go through the lecture. And Wednesday, we'll have a class on LDA is the topic I'll cover. And then, so Wednesdays we'll cover classical ways of doing. Mondays we'll do the deep learning way of doing.